Hello, my name is Russell Brubaker. Today, it will be my pleasure to talk to you about the research I have been conducting over the past year. Under the mentorship of Dr. Frank Rahill and Dr. Brian Maitland, I have been using stable isotope analysis to explore sulfur isotopes in the Laramie River. Stable isotope analysis offers us a unique way to investigate how elements and nutrients flow through organisms and ecosystems. Technological advances are increasing the affordability and availability of the analysis of certain isotopes, opening new avenues for understanding our natural world. So, what are stable isotopes? While an atom's element is determined by the number of protons in the nucleus, an isotope is determined by the number of neutrons in the nucleus. For many elements, there are two or more stable, non-radioactive isotopes. Each isotope has a unique molecular weight which can subtly influence how it interacts with various chemical reactions. For each element, the lightest stable isotope containing equal numbers of neutrons and protons is the most abundant, with heavier isotopes being more rare. Natural abundance is a measure of the average amount of a given isotope across the planet. Stable isotope analysis relies on observed deviations of heavy stable isotopes from their natural abundance. Traditionally, carbon and nitrogen have been the most important isotopes in ecological studies. Carbon is fixed during photosynthesis, which favors lighter isotopes, and different types of plants have different fixation rates. For example, aquatic plants have less heavy carbon than land plants. The ratio of heavy nitrogen isotopes increases with every step up the food web. Predators have more than herbivores who have more than plants. By comparing the isotopic ratios of carbon and nitrogen in the organisms in an ecosystem, we are able to construct a plot that helps us to visualize a food web for that system. These plots help us to understand the important predator-prey interactions as well as how basal resources flow through the system. While carbon and nitrogen isotope analysis can give us a detailed look at important food web interactions, they are still limited and sometimes lack sufficient detail to tease apart other relationships. In this example, we can easily visualize the niche of the creek chub in green, but the minnows and sucker on the bottom appear to be existing in the same niche. Fortunately, carbon and nitrogen are not the only multi-isotopic elements common in biochemistry, nor are they the only elements which experience biologically driven isotopic fractionation, leading to deviations from natural isotopic ratios. Thanks to advances in mass spectroscopy, it is now affordable to investigate these other isotopic relationships. Sulfur offers some exciting possibilities as a third isotope. In the absence of oxygen, certain microbes can use sulfur compounds instead of oxygen to carry out respiration. The metabolism of these anaerobic sulfur reducers enriches the natural abundance of heavy sulfur isotopes, leading to spatial variations in sulfur isotope ratios. Sulfur isotope analysis isn't new. In several studies, it has been found to be very useful in the analysis of large marine systems. However, sulfur has not been well studied in smaller freshwater systems, such as rivers. The small spatial scale and heavy mixing activity of rivers could potentially homogenize and obliterate any sulfur isotope gradients. Despite the potential challenges, I wanted to investigate the efficacy of sulfur isotope analysis in a river system. Under the guidance of my mentors, I collected several fish, invertebrate, and sediment samples from the Laramie River to conduct my own ecological isotopic research. For the purposes of this presentation, I will focus on what I learned from the fish that were collected. In this chart, you can see how many of each fish species were captured. I was well pleased with the collection as we had a near perfect representation of all the species present in the river. Only the Iowa darter and long-nosed sucker were missing, neither being very common in our region. With collection completed, I began meticulously cataloging specimens, collecting, dehydrating, and processing muscle tissue samples to be weighed and recatalogued for each individual fish and invertebrate. After the prep work, the samples were submitted to the University of Wyoming Stable Isotope Facility for carbon, nitrogen, and sulfur isotope analysis. These graphs give us the first look at the raw data from the fish I collected. From left to right, we are comparing carbon to nitrogen, sulfur to nitrogen, and finally sulfur to carbon. Right off the bat, we can see that we have a wide range of sulfur values, and there appear to be some very distinct patterns relating to sulfur. With further analysis, we can start to tease apart the patterns. In the bottom left corner, we have the same three scatter plots from the previous slide. The line graphs running diagonally through the middle are showing the density distribution for each individual isotope, and the graphs in the upper right are showing several random niche regions generated by a Bayesian statistical analysis of our data. For this graph, I have chosen to analyze just 3 fish for the sake of simplicity. As you can see, with a traditional carbon and nitrogen analysis, it is nearly impossible to differentiate the niche regions for brassy minnow, fathead minnow, and white suckers. However, with the addition of sulfur isotopes, we are able to observe clear distinction between the niches. Looking at the same 3 fish, the set of graphs on the left shows the probability of niche overlap looking at just carbon and nitrogen, while the graphs on the right show the same statistical analysis but with all 3 isotopes. The highlighted histograms show that just looking at 2 isotopes, the brassy minnow's niche appears to be nearly completely overlapped by the white sucker. However, looking at all 3 isotopes, there appears to be nearly no overlap. Invertebrates were excluded from the study due to our sample being a poor representation of the river's invertebrate taxa, with multiple groups being represented by only an individual. Despite this, looking at the limited invertebrate data offers some tantalizing evidence that the invertebrate community may hold the key to understanding sulfur isotopes. Future research should put heavy emphasis on them. In conclusion, this study has shown that sulfur isotope fractionation is clearly present and measurable in the Laramie River, and that measuring patterns in sulfur isotope ratios does add resolution to a traditional isotope analysis. However, while this research is an exciting step forward, there is still much to be understood about which factors are driving our observations of sulfur isotopes. I would like to thank my faculty mentor, Dr. Frank Rahill, and his doctoral student, Brian Maitland, who completed his PhD during my research. Their combined knowledge and experience were the driving force behind my dedication to this project. Dr. Annie Bergman, for her tireless effort to provide these invaluable opportunities for students like me. I would like to thank the Wyoming Inbray and the Vern Bressler Fisheries Fund for their help funding this project, and the University of Wyoming Stable Isotope Facility. Thank you for watching.